We're going to wrap up all of our lessons about covalent bonding by talking about intermolecular forces. And this will bring in all the concepts together. And we call them IMFs. That's not the impossible mission force. That is just the intermolecular force. So the intermolecular forces are the stickiness of the actual molecules. I've called them stickiness before, but now we're going to start calling them intermolecular forces. They are the forces of attraction in between molecules themselves, like hydrogen, like a hydrogen bond right here. This is responsible for why water is so sticky to itself. So they are the forces that act between different molecules that are called intermolecular forces. Now, these are the forces that make solids and liquids. So as you know that solids have the least amount of kinetic energy, and then if you add a little bit more kinetic energy, that will actually start to break apart the molecules because it overcomes the intermolecular force. It overcomes the stickiness of the molecules. So now the molecules are able to flow past one another and become a liquid. And then if you add even more energy, you get to this point, you now have more energy than the intermolecular forces allow, or the strength of the intermolecular force. And so the molecules will separate and you end up as a gas. So this is really the key of why we see solids, liquids, and gases, and why the boiling and melting points change based on the molecules. So just to review, be very careful to understand that intermolecular forces are the forces in between molecules. Now, they are weaker than the intramolecular forces, and those are the chemical bonds within the individual molecule. This is a big distinction here. So intermolecular forces are between molecules themselves, from one molecule to another, or one particle to another. Now, an intramolecular force is inside the actual molecule. So from a covalent bond, like from an oxygen to a hydrogen. So like an interstate highway goes in between different states, and an intrastate highway would be something like Highway 6 that does not go between states. It only stays in Texas. You could think of the internet or an intranet as well. An internet connects computers, and intranet is more of just computers on a single network that doesn't connect to the outside. So hopefully we're understanding the difference. We really only talk about intermolecular forces though. So there are three of them, and they're given in order of strength right here. So hydrogen bonding is the strongest, and they are actually a special case of a dipole-dipole. So dipole-dipole is right here. It's not dipple-dipple. And then there is the London dispersion forces. So the London dispersion forces are the weakest. Hydrogen bonding is the strongest. So just a little bit of warning right here. There's some different terminologies here. IB likes to refer to all of these as van der Waals forces. But in AP, they only refer to the London dispersion forces as the van der Waals force. So van der Waals is obviously a person. Sometimes I've heard it called van der Walsh, but van der Waals forces is typically what we're talking about is just the London dispersion force. So we're going to go a little out of order, but I promise it makes sense. So the dipole-dipole forces are the electrical attractive forces that exist between polar molecules. They must be polar for it to be dipole-dipole. They are the attractive forces are stronger than the repulsive forces. So there's an overall attraction between the molecules. What happens is that there's a negative and the positive end in a polar molecule, right? You've learned this before. So another molecule will come up here and it will align itself so that its negative end is facing towards the positive end. And so two different molecules will actually attract like this. And so this positive would actually probably try to attract to this negative end as well. And so they get a little more sticky, and it's simply just because two polar molecules are aligning each other so that they are the attractive forces are the strongest and the repulsive forces are the weakest. So hydrogen bonding is a special case of dipole-dipole interactions. So this happens is when hydrogen is directly bonded to a highly electronegative atom. There are only three of them: fluorine, oxygen, or nitrogen. So it must have either fluorine, oxygen, or nitrogen to be hydrogen bonding. And that hydrogen has to be directly bonded to one of these. So a good example of this is water. Water has oxygen, and then hydrogen is directly bonded to oxygen right here. And so this is not a hydrogen bond, by the way. I'll show you a picture in a second. But you see water right here, and you see their partial charges, and you see a very big partial negative charge on this side, and then partial positives over here, which is meaning that there's a big electron density over here, which means it's going to attract to something that's electropositive, like another water molecule. I'll show you a picture. So you have two different water molecules right here, or three different ones. And so the oxygen is actually going to align itself facing towards the hydrogens. Hydrogens align themselves facing towards oxygen. Oxygen facing towards hydrogens, okay? And so we represent this dash right here, or these three dots, as the hydrogen bonds. Now these are actually weaker than the bonds in between here, but they are still the strongest of the intermolecular force. So an intermolecular force is the attraction between one molecule and another molecule. So just to be clear, this is not a hydrogen bond, okay? This is just a covalent bond in between hydrogen and oxygen. This is the hydrogen bond, okay? It is a bit of a misnomer. I just want to make sure everybody is clear on that. So just remember that hydrogen bonding only exists between fluorine, oxygen, and nitrogen. Now the way you remember that is you can't hydrogen bond without a phone, F-O-N, a phone. Okay, so hydrogen bonding is responsible for a lot of special things about water. Water as a liquid is a lot more compact than it is as a solid. That is because the hydrogen bonding is actually going to put it into that hexagonal shape and make the volume a little bit larger, which makes the density go down. So you see that the density of water actually starts to decrease as it starts to get colder and colder. So ice is actually less dense than liquid water. And it's one of the very, 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 very few substances that will actually do that. So this is why lakes freeze at the top first. And it's very nice for fish because it's a little warmer down here, so the fish can survive. And it's also nice for ice skaters. So the last force we're going to talk about, we talked about dipole-dipole, we talked about hydrogen bonding. And the last force is called the London Dispersion Forces. Now, this is not named after the city, it's named after a person. So London Dispersion Force, let's just consider a symmetrical molecule like hydrogen, H2, or bromine, Br2. And we have a nuclei here and a nuclei here. And then the even shading shows that on average, there's no electrical charge. So the force is not good, or it's not the dark side, it's not the good light side, okay? And then, however, the electrons are mobile, and then at any one instant, they might find themselves towards one end of the molecule, making that end negative, it's gone to the dark side, and the other end positive. It's gone to the light side, I suppose. So this is called a momentary dipole, okay? Now, an instant later, it will switch back. So this one is now gone to the dark side, and then this one has now switched, okay? So you see that going from here to here, even though they're both Anakin, one of them is gone to the dark side, one of them is not quite yet on the dark side, okay? So this constant sloshing around of the electrons in the molecule causes rapidly fluctuating dipoles, okay? even in a symmetrical molecule. So there's wishy-washy between the electrical charges. So this even happens on noble gases like helium. Helium can have a momentary dipole as well. So even noble gases will do this. So if you have something that's here, imagine a molecule which has a temporary polarity. When being approached by another molecule, that's going to take this molecule right here, this nonpolar molecule, and cause it to be induced as well. So what this one was the original one. This was had a negative charge and a positive charge. So then that's going to actually make this one be a negative charge and then a positive charge. And the pattern can continue to another molecule. So one molecule can affect the molecule next to it. So this is called an induced dipole right here. And so they'll switch back, but will create some type of attractive forces. So an instant later, they will switch back, and then they will start to reverse again. So you see the London dispersion forces are really just the sloshing around of electrons, and it's just saying that the molecules will wiggle just a little bit, and so that they will attract at some point. Now again, London dispersion forces are between non-polar molecules. Non-polar molecules, the only intermolecular force they do is the London dispersion force. That's a key thing. You might want to write that one down. So if you're still not understanding London dispersion forces, you can think about a whale watching trip. So if you were standing on a boat right here, and you're waiting on some whales, and you're really bored, you wish the whales would show up, and then somebody shouts, "Hey, look, there's a whale." And then everyone on the boat moves to that side of the boat. All right? And now any other boat that's next to it is also going to move over to the same side of their boat because they want to see the same whale that you saw. Right? And then, so that will cause everybody else to run to that one side. And then once the whale's gone, everybody will kind of drift back to the middle, and then we'll look again for another whale until the pattern continues. And so everybody kind of moves to one side of the boat, and then to the other side of the boat, and then backwards. Hopefully you're kind of getting the idea of what London dispersion force is. Now, it's important to understand that all dispersion forces, all molecules have London dispersion force. They act upon all molecules. So they're essentially the participation ribbon. Everybody gets one. They're only important when they are the only force acting. So it's essentially only when it's a nonpolar molecule is when we really start caring about them. So here's some nonpolar molecules just to let you know. They tend to increase in strength with an increased molecular weight. There's more sloshing around, so there's more of a attraction between them. So something like octane is going to have more London dispersion forces or more attractiveness than something like ethane right here. Something like, I think this is neon, and I think this one is xenon or argon. It has more protons, so it's heavier. And so you'll get more of a sloshing around, you'll get more of an attraction because it has more electrons. All right. This actually explains why the halogens are different colors. If you look at your periodic table, the fluorine and chlorine, halogens are all what we call diatomic, which means that they bond with themselves. So you see fluorine bonded with fluorine, chlorine bonded with chlorine to make Cl2, Br2, I2, acetine 2, At2. So they're all nonpolar molecules, so they only have London dispersion force. So the heavier that they get, the greater the intermolecular force it is, and so the higher the melting point gets, or the higher the boiling point gets. So just to kind of compare the strengths of forces, I know we've talked about a lot. Your normal covalent bonds, which are an intramolecular force, that's not really in the scope of this lesson, are let's say the bond strength would be 400 kilocalories. And then hydrogen bonding, the next strongest, that's an intermolecular force. They would be between 12 and 16 kilocalories. And then dipole-dipoles are a little bit weaker. And then London dispersion forces are much weaker. So again, this just gives you an idea of the scope of how attractive they are. Covalent bonds are still much stronger, and then ionic bonds are even stronger than the London dispersion forces. They're very weak, but they do play a role. So just to recap, hydrogen bonding is a polar molecule that has hydrogen directly bonded to either fluorine, oxygen, or nitrogen. A dipole-dipole interactions happen between polar molecules attracting to one another. And then London dispersion forces are nonpolar molecules attracting to one another. Essentially, just remember that slide and you will be good to go for the test. You may have to be, this helps you, the theory helps you understand this slide. So let's try to get a few examples. Let's start with the old classic water. So we draw the Lewis structure first, just to get an idea of what it looks like. And then we'll figure out its polarity. Well, we know that water is polar because it has it's a lopsidedness of charge. It has lone pairs in the central atom. So now its strongest intermolecular force is going to be hydrogen bonding. So the intermolecular force could have been either dipole-dipole or hydrogen bonding because it's a polar molecule. But since hydrogen is directly bonded to oxygen, then it is going to be hydrogen bonding. Now let's take a look at nitrogen. Its Lewis structure looks like this. So now let's think. Is it has a symmetrical structure, symmetrical electron structure. So then it's going to be nonpolar. That means it can only be London dispersion force. So hydrogen sulfide or dihydrogen sulfide, its Lewis structure looks like this. Looks very similar to water. So it's going to be polar. So it could be either hydrogen bonding or dipole-dipole. So which one is it going to be? It's going to be dipole-dipole because hydrogen bonding requires there to be either fluorine, oxygen, or nitrogen. So that is not either one of them, so it's only going to be dipole-dipole. So CH3Cl, draw the Lewis structure here. And so that one's going to be polar as well. And we're going to call this one dipole-dipole. That is, there is a polar molecule right here. However, there is no hydrogen bonding taking place. So let's look at methanol, CH3OH. Here's the Lewis structure. Now go ahead and see if you can figure out the polarity in the strongest intermolecular force. I'll wait. Welcome back. You should have seen that it's polar, okay? Polar in respect right here. And so this one will actually have hydrogen bonding. You have a hydrogen that's directly bonded to an oxygen here. All right, now let's try this, guys. Something that looks similar, CH2O. That drawing's fun. So it is going to be polar. Now, what is the strongest intermolecular force? Some say it might be hydrogen bonding. However, it's a trap, okay? Because there is oxygen present, yes, and there is hydrogen present. So students will think, oh, that must be hydrogen bonding. However, this hydrogen is not directly bonded to an oxygen. So this would be a dipole-dipole attraction. So let's try one more time. You even know it. It's a trap. It is CH3F. So it is a polar molecule and it is dipole-dipole. All right. Have a great day.